My name is Hamoudi Awde. I'm a PhD student at National University of Cordoba, Argentina. Today I'm going to talk to you about dexamethasone loaded nanostructured lipid carriers for ophthalmic applications. First of all, ocular therapy usually have a problematic due to the natural anatomy and physiology of the eye. Also, usually when we talk about inflammatory processes, we use drugs that has low absorption and low solubility, making the pharmacotherapy even harder. Under these circumstances, we propose the nanostructured lipid carriers as a platform for loading of corticosteroids, in our case, dexamethasone. Nanostructured lipid carriers are basically an evolution of solid lipid nanoparticles, whereas we also add a liquid lipid for the matrix, meaning we have a nanoparticle with high encapsulation of drug, biocompatibility due to the lipids we choose, control release. The procedure for preparation of these nanoparticles is free from organic solvents, and the procedure can be scalable to an industry. Also, by adding the liquid lipid, we improve the drug entrapment, we reduce drug expulsion, and we also allow the loading of hydrophilic molecules. The method to preparate these nanoparticles, basically, we have an aqueous phase and a liquid phase. In the liquid phase, we have both the solid and liquid lipids melted with the drug, and in the aqueous phase, we have water and the surfactant. To standardize this method, when we did the ultrasonication method, where we use a group sonicator generating cavitation procedure, meaning that we break droplets till we have droplets in a nanometric scale, we needed to standardize the proportions of surfactant and solid and liquid lipids. Under that assumption, we create a mixture design using the Minitab software, where we made different formulations with different amounts of surfactants and different amounts of lipids. After that, we create the we find the best possible combination to achieve the best nanoparticle. After that, we load it with dexamethasone and start the characterization of the nanoparticle. As we see, we have good colloidal stability at least for the first 60 days of analysis. Also, we have a high drug encapsulation efficiency close to 100%. Also, we realized that DXM, or dexamethasone release, was controlled in comparison with dexamethasone alone, meaning that we had a good nanoparticle with 60 nanometers of size, high drug entrapment, and control released. Also, we needed to evaluate if there was any chemical changes in the nanoparticles. For this, with this in mind, we lyophilized we freeze dried the nanoparticles, and we did the next assays. For the XRD, or crystallography, X-ray crystallography, we evaluate the different components. For example, the physical mixture, the nanoparticle, the blank nanoparticle, meaning with no DXM, and DXM alone. The same for the thermal analysis, and the same for the FTIR, or infrared spectroscopy. After analyzing this, we realized there was no chemical changes, no apparent drug expulsion, and we found that there was drug solubilization in the lipids, of course. Afterwards, when we already characterized the nanoparticle, we evaluate the in vivo efficacy. To do this, we use a model called endotoxin induced uveitis, where what we do is we inject intravitreal LPS, that is Escherichia coli lipopolysaccharides, inducing the inflammatory processes in the eye. This is an acute model. It's not chronic, meaning that after 72 hours, usually the eye recovers by itself. So we created a clinical score, evaluated things like corneal damage, conjunctival redness, Tyndall effect, vitreous damage, iris, etc., etc., etc. The primary the parameter that we see is the flare. that is the aqueous humor nuosity in the anterior chamber. For example, you can see here that the anterior chamber it's completely transparent in comparison with crystalline and the cornea. And when we analyze an eye that has uveitis or an inflammatory processes, we can see that that transparency it's reduced. That's what we call flare effect. So after the induction, we applied subconjunctively, I mean by subconjunctival injections, both uh, dexamethasone by itself, a suspension of dexamethasone, a suspension of the nanostructured lipid carriers, normal saline solution as a control, and of course, we evaluate the three things. After 72 hours, we realized that the clinical score of the rabbits that were treated with our nanoparticles show less clinical score in comparison with both dexamethasone treated and the treated with normal saline solution. After that, we took pictures of the eye using specialized equipment for that uh, for that purpose, we had the help of an ophthalmologist of our group when he used a special lamp that allows us to take pictures of the anterior chamber. So what we do is we proceed to process the pictures in a great scale, and we evaluate the density of pixels in the anterior chamber pictures. In that way, we construct something called aqueous humor transparency. And as I told you before, the more transparent the anterior chamber means that the eye is more, it's a sane eye, we can say. So after treatment, we realized that those rabbits that were treated with our nanoparticles showed a better transparency or a more transparent anterior chamber in comparison with both treated with dexamethasone and the treated with normal saline solution. So after 24 hours, the nanostructured lipid carriers loaded with dexamethasone significantly reduce inflammatory response in the anterior chamber. As such, we can realize that by loading dexamethasone in the nanostructured lipid carriers, we allow drug solubility, meaning that we increase bioavailability, permeability. Also, we reduce the required dose because in our in vivo model, we use less drug dose that we usually use in clinic. Also, these nanoparticles are efficient for administration. They are easy to sterilize. And we also have a versatile platform because we are planning of loading other molecules inside these systems. So thank you very much. I hope my, my English was understandable, and have a good day. Thank you very much.